Section 6.3, uniform circular motion example with a bicycle going around a vertical loop. This says, this is one of my favorites. In a 1901 circus performance, Allo Daredevil Diavolo introduced the stunt of riding a bicycle in a loop-de-loop. Assuming the loop is a circle with a radius of 2.7 meters, what is the least speed v that Diavolo could have at the top of the loop to remain in contact with it there? All right, so this is awesome. Perhaps not the most practical, but things don't have to be practical to be cool, right? So where are we focused in this problem? We have this nice classic banner here. It says the top of the loop, right? So the top of the loop, we could imagine the bicycle right now is at the top of the loop. What are the forces acting on Diavolo at this top of the loop? Well, we have gravity, right? Gravity's pulling down, cool. Can't get rid of or change the force of gravity. Any other forces? The other force we could have is the normal force. Now, what's the direction of the normal force in this case? Well, notice because the bicycle is on the inside of the loop, it's not on the outside like our Ferris wheel example, the normal force is actually pushing down on the tires. So we now have two different forces pushing down, which seems like a problem. Well, it certainly makes it challenging to stay in the loop. That's where you have to keep traveling fast enough so that by the time you fall in, the track is still there as you're moving forward enough. But we can go ahead and make a free body diagram of this, right? Where we have the force of gravity pulling down on Diavolo, F sub g, and then the normal force is also pushing down. All right, the other thing we want to consider is if there's any acceleration present. So for acceleration, we remember that would be, we can write it off to the side. It's not one of the forces. And because we're traveling in a circle, we should have some acceleration towards the center. So in this case, it's the same direction as the forces, which is actually a good thing, because it'd be hard to create an acceleration any other direction. And so we can look at, hey, this net force has to equal the mass times the acceleration here. So, okay, so F net in the y direction is equal to the mass times the acceleration in the y direction. And in this case, we could make the negative y, the downward direction is positive, and then everything would be positive, or you could just make everything negative. It's the same difference either way. So if we make down negative fg minus the normal force is equal to mass times this negative centripetal acceleration, right? We know that we have to have centripetal acceleration here, so it's going to be our v squared divided by our r radius. All right, so everything here is just going to become a positive, so the negatives cancel out. There's much rejoicing. That's all well and good. Now, we're solving for v. We know the radius, we don't know the mass, we don't know the normal force. But we do have one other clue, and this is where this problem gets a little bit trickier, hand-wavy. And that's noting that it asks for the least speed v. If it's the very least speed, this is going to be the limit where the bicycle is barely in touch with the ramp, right? Where Diavolo is just starting to fall. If he's going any slower, he would no longer be in contact with the ramp. So at this least speed, whoops, sorry about that, the normal force is going to be 0. Because that's where it will barely be in contact. If we're going any faster, that will actually push Diavolo more into the track, because the track will push down harder. Because once you start going faster, you have a larger centripetal acceleration, so you have more downward force. So the least speed is where the normal force is 0. And once we can make that conclusion, the rest of the problem becomes very simple, because we have the force of gravity is mg is equal to mv squared over r. That means our m's are going to cancel. And so then all we have to do is solve for our v squared over r. So multiply the r times the g and take the square root, and we are home free. So we have that the speed is the square root of g times r, and that comes out to 5.1 meters per second of how fast Diavolo needs to be going at the top of the loop. And we can actually, later on in the semester, we'll be able to do the calculation of how high up Diavolo needs to start in order to get to a speed of 5.1 meters per second to stay in contact to complete the loop-to-loop. So all the practical skills here in physics. This one is just a fun example and cool to see how it can work. So there you have bicycle going around a vertical loop. This is something, by the way, that skateboarders now are doing. You can YouTube it. Super fun.